Hello, my dear warriors. Welcome, welcome. Hello, Pradeep. Hello, Philo. Hello, Harborine. Hello, Krishna. Hello, Dinesh. Good morning. Good morning, Madhumati. Good morning, Philo. Good morning, Alekhya, Satyashri, Tejaswini, Prajwal. Hello, Sumi. Hello, Satyashri. Good morning. All the warrior pandus. Welcome aboard to the next lecture of your RNA series. Yes, Roar NEET Aspirant series. And this is where we do all the concepts and also some problem solving on all the topics or all the chapters that are at hand. So the next chapter, after completing relative motion, motion in 2D, motion in 1D, vectors, basic maths, all these chapters, next chapter is Newton's laws of motion. After this chapter, we'll be moving on to circular motion. But Newton's law, I'm dividing it into two parts. The first part today will be mainly on the forces, free body diagram, normals, or tensions or the weights, finding acceleration or equilibrium problems, those kinds. In the next part, I'll be doing mainly friction problems, block on block problems, contact force problems, those kind of questions, and multiple pulleys, if at all any. Okay, so we'll be dividing it into two parts, right? So today's, think of it like part one, right? So Vanakkam, Mr. Horiki, hello, study only, hello Akash, nice to see all of you over here. Lovely morning, nice start of the evening, nice start of the month as well. So before we proceed ahead, let me just do a quick reminder about MVSAT, which is a scholarship admission test at Vedantu, which is going to happen very soon, but you need to start registering for it. It's available both in the online and offline mode. And why you should register for the MVSAT is because there are lots of prizes to be won, lots of gifts to be given, lots of discounts to be offered on variety of things. And even if you are already a part, at least you can get some rewards and prizes. That's the reason why you should be a part of MVSAT. So guys, also you will be testing among lots of students. So you will know where you stand at this point of time and see and compare your all India ranks. Maybe you have a friend who is studying in some other institute. Maybe you have somebody doing a self-study. That's a good way to assess where you are at this point of time, because you might be rank 10 in your coaching, but maybe at a different national level, it could be way different. So it's a very good way. And obviously scholarships are there, lots of prizes are there. The links for registering are there down in the description box below. So make sure you check it out and register for the MVSAT as soon as possible. Okay, great. And spread the word around. So let's begin with your Captain Shreyas. All right. Rotational motion will take some time. Obviously, probably by the month end or maybe by start of next month. Okay. But yeah, it will happen within a month or so. Okay. So let's start with this. See, in this chapter, we deal with different kinds of forces which are there around us and how to, analyze the motion, why things move the way they are. Now, there are fundamentally 4 different forces in nature. So I will call them as fundamental forces. Fundamental forces or basic forces in nature. What are those 4 forces which I am talking about? Well, first one is gravitation. Next one is basically electromagnetic forces. And then you have over here, there are 2 kinds of nuclear forces. One is basically the weak nuclear force and strong nuclear force. These are the 4 basic kind of forces. In NEET syllabus, you just study gravitation and electromagnetic. In NEET syllabus, you do not study these forces, although you listen or hear about it in few lines in the last chapter of 12th standard physics. A little bit, but no formulas or no much information as such on this particular part will be given to you. Okay, it is not a part of a NEET syllabus. It's much beyond that. You go at MSc level, then you study it. So These are the main two forces which we deal with in our day-to-day life. Why we don't study is also making sense, because in our day-to-day life, somebody slaps somebody. It's not nuclear force. I am pulling something. It's not nuclear force. It is electromagnetic, or I have my own weight, body weight. Okay, Earth is pulling the moon. So those are gravitational forces, or at the end of the day, electromagnetic forces. That is what you encounter in day-to-day life. That is why we study these two. You will see that gravitational force is actually a very long range force. This is very long range force as compared to this one, which is a very short range force, So here the range becomes long as you go. The door. Yeah, as you go down below over here, the range becomes very short distance. Nucleus, inside the nucleus it can apply. Beyond the nucleus, it has no effect. Gravitation, Earth can pull the moon, sun can pull the Earth, such large distances. Electromagnetic, not so long range. You know, two magnets can attract each other maybe at this much distance, but not so much distance. So that's why little bit short range. So as you go here, the range becomes short. But they say when life takes away something from you, it always gives you something. And you might have also felt the same. So if this range is short, no issues. This is the strongest force in nature. These are basically the strongest in nature. So as you go down, it becomes strong. As you go up over here, it basically becomes weak. Gravity. Imagine Earth being so huge, moon being so huge, then they attract each other. But electrons, protons, so teeny mini, and they are able to attract each other, so they are little bit stronger. Nucleus, even very small, and they are able to apply very strong forces, even much more than the gravity or electromagnetic. So that's why they are strongest in the nature. Yep. I hope this is absolutely clear. When you combine these forces in different ways, in different forms, right, then the kind of forces that you get are basically derived forces. A combination of them, a combo or a manifestation of them is basically called as derived forces. This is basically called as derived forces. And the examples of this are basically weight, normal, contact, tension, spring, elastic, all these forces, magnetic, etc. All these forces are basically a combination of these forces. So you take these forces and you combine them together, then you get weight, or maybe just a manner in which you see them, manifest them. When I'm standing on the earth pulls me, it's gravitational pull. But that is what I call it as the weight. That is what I call it as the weight of an object or the weight of a body. Okay, so I hope this is very clear. This is fundamental forces, which are 4 in nature. One is strong, one is weak, one is long range, one is very short range. A combination or the manifestation of them is the derived forces, which we are going to focus on. Right? Till this point, everybody clear? Okay. Now, since you have an idea of what forces are, there are 3 main laws of Newton which we will study, and through very simple animation, and that is none other than our, where is it? PHET. Yes, let's go to PHET and let's go to the simulation part, and you will see a very interesting simulation on this. Where is it? I just want motion. Okay, just go to motion and let's go down, forces and motion basic. It's a beautiful simulation which you're going to see. Okay, now let me show you a very interesting thing. This is a box, this is a person. This simulation can play around with different things. I can apply force and it can begin to move. I can apply force in the opposite direction, it can stop and it can go in the opposite direction. I can make it more rough and it will stop very soon. All these options are there. I can see the mass, the values, the speed, everything. Okay, beautiful simulation. The point is, see what happens when I apply some force. Okay, let's apply some force on this box and let's keep pushing it. The box is under motion. You can see the speed is increasing. I remove the force. The speed is slowly reducing. The motion is not uniform. The motion is non-uniform motion. It is velocity is reducing and eventually the speed becomes zero because there is an unbalanced force. This is an unbalanced force. Here, this is also unbalanced force. You can see why. I am applying more force. Friction is, oh my god, this guy gave up. Sorry guys. So that guy gave up. You saw he fell down. Poor fellow. But this is also unbalanced force. This is also unbalanced. Why? Because they do not cancel each other. They do not cancel each other. But imagine I apply exactly same amount of force as that of in the opposition, as whatever is being opposed. Then I will see, say for example, let me increase the force slowly. Yes. 118 Newton, 118 Newton. Do you see what is this object doing? It is moving with a constant speed. It is moving with a constant speed, my dear students. This is a set of balanced forces which cancel each other. Vector addition of all the forces is zero. So what happens when the forces are balanced? Nicely it is. Forever it will keep moving. It will not change its speed. It will not change its direction. It will be like, okay, let me keep moving. But the moment I increase something, it will now slowly, you can see the speedometer is changing. It is a non-uniform velocity. Velocity keeps on changing. Again, if I reduce it, now it will maintain that new velocity. It will maintain that new velocity. I get rid of this person. Get rid of this person. Bye bye, Tata is gone. Unbalance. Unbalance means velocity will definitely change. So balanced forces basically maintain the situation, the state of motion of that body. Unbalanced forces change the state of the motion, change the momentum, and how much ever force you apply, decide how quickly the momentum would change. Decide how quickly that momentum will change. We can see that over here. If I apply this much, 200 Newton of force, okay, speed is increasing slowly. If I increase that force even more, the speed increases faster. The speed is increasing faster. So more force applied increases the momentum of the system at a much faster rate. Whatever I told before was actually Newton's first law. Whatever I told now is actually Newton's second law. Newton's first law says that as long as, you know, the applied forces cancel each other, the body maintains its state of motion or uniform rest. It is maintaining. It is maintaining. It will keep moving. You see it after 2 years also. This guy will be pushing this, assuming my board is still working. And the second law says that the moment there is an unbalanced force, the net unbalanced force is proportional to how quickly the momentum changes. That is your Newton's second law. Are you able to visualize this? Are you able to see this practically? Yes or no? Are you able to see this practically? Yes or no? Everybody give me a thumbs up and smash the like button if you have not done that yet and not yet subscribed. Do that right now. Not yet subscribed, do that right now. You might wonder, sir, what happens if friction is not there? Wow, it became so slippery. It's become icy. It's become icy, guys. Nothing is there. So now, if you push it, wow, it is accelerating so quickly. I leave it. Tata, bye bye. This guy is maintaining the speed. Why? There are no forces. Any force being there, it is anyways cancelling. If normal is there, gravity is there, they are cancelling each other. All the forces are cancelling each other. Nothing unbalanced is there. So it is maintaining. Forever it will go on. But the moment there is an unbalance, zoop, there you go. It's reducing. its momentum or changing its momentum, and it stops. That's your second law. Perfect. So let's write it down. So Newton's law of motion, the first Newton law of motion says that if the net external force is zero, basically balanced forces. Balanced forces means that you have some object, there could be multiple forces on it. There could be multiple forces on it, but they all cancel. The vector sum is zero. So this is a set of balanced forces. Then I will say, then the body maintains its state. Body maintains its state of uniform motion, or basically rest. It maintains. So whatever velocity it had, that velocity will remain constant. That velocity will remain constant. That is your Newton's first law, my dear students. Very good. Next one. The second Newton law of motion says that if I have some body, but I find that the forces are unbalanced, meaning they do not cancel out each other. So maybe there is a net resultant force. So this is your F net. This is your F net force, which is nothing but the vector sum of all the forces, F1 plus F2 plus Fn. And since I am saying it is not zero, that means it is the unbalanced force. So Newton's second law says that the net unbalanced force is directly proportional to something called as the rate of change of momentum. That is what it is proportional to. That is your Newton's second law. That is what it says. Nothing more, nothing less. Correct. Now you can play around with this. The net force being F net. I just said the net force is proportional to the rate of change of momentum. Whenever I use the word rate of change of something, it means it is the derivative. Of that. So rate of change of momentum means it is nothing but dp by dt. I do not want proportionality, I want equality. So I'll just put k times dp by dt. But what is momentum? Momentum is nothing but mass times the velocity. Perfect. Now when I have to find the derivative of two things which are multiplied, use the product rule. So it will be m times dv by dt plus v times dm by dt. uv rule, guys. u v dash plus v u dash. So first function into second's derivative plus second function into first guy's derivative. Now what happens usually is that, see, dv by dt is nothing but acceleration. So I'll just put acceleration over here. This dm by dt is usually zero. Why? Because these systems where dm by dt happens to be a big fat zero, they are said to be constant mass systems. Mass is constant, so the derivative is zero. Many systems are like that. I take a block, I push it, block's mass won't change. I'm taking a cart and pulling it, the cart's mass won't change. An apple is falling from the tree, the apple's mass won't change. A bird is flying in the air, the bird's mass won't change, though it will change after a very long time because, you know, of the digestion and maybe respiration, and some oxygen went in, that bird, you know, dropped something, it ate some worm. So that mass changes can happen, but that is very minute. Also, there are cases where masses can change significantly. For example, there is a train. it stops at a railway station. Hundreds of passengers will get inside. The mass of the train will increase significantly. Or maybe there is an aeroplane which is flying. It carries so much of fuel. After flying for some time, that fuel will get burnt. So the mass will reduce. People get down from the plane, mass will reduce. Correct? Rocket is flying. Slowly you might have seen the pieces of rocket fall off as different stages of rockets happen. So you will see when rocket fuel is burnt and different stages occur, so much of mass gets changed. So those are variable mass systems. We do not have such things in the NEET syllabus. So don't break your head over it. Yes, so we just have mass being constant. So all we get over here is the net force being nothing but K times of M times of A. What is this K? K is just a constant, but we can also get rid of it. We can say we define the force of 1 Newton. So 1 Newton force is when a mass of 1 kg accelerates by 1 meter per second square. In such a case, 1 will be equal to K into 1 into 1. Therefore, K will be exactly 1. So therefore, in our SI system of units, our net force becomes equal to the mass times the acceleration. This is the simple way of writing the Newton's law, second law, in a very simple manner. But actual Newton's second law is this one. It is not F is equal to ma. It is a modified version of the second law when mass is constant and you don't want momentum in the equation and all of that. Is that right, everyone? Great. So that is Newton's second law. Newton's first law we already saw. If net force is 0, velocity is constant. Now, let's go to the third law. Of course, this guy is still moving. See? Okay. Let's go back maybe a little bit. Let's again come back over here. Okay. So maybe let's see over here. Oh no, not this one. My bad. This is a very, very nice question, guys. Let's get one person over here. Let's get one Chintu Mintu person over here. Okay. Let's put values sum. Okay. All right. Let's forget that. Let's start a tug of war. When I press go, I think the tug of war will start. Okay. So guys, tell me one thing. In this tug of war, this guy, huge, bulky person, this guy, Chintu Mintu person, I'm pretty sure tug of war will be won by the blue person. So if I say go, you can see in this process, the tug of war is won by the blue person versus the red person. Oh my God. They won? Yes, the blue wins. Perfect. It should happen. Let's return them back and you can see why it should happen. Because the guy on this side applied more force, the guy on this side applied less force or was not able to hold it so much, and the resultant force was towards the left side. Okay, perfect. Because of which, the blue person won over the red person. Now, when this is happening, this 150 and 50, is it the force which the person applies on the rope or the net force which the person applies or the net force which the person experiences? Think about it. Is this 150 and 50 Newton the force which each of these people apply on the rope, or is it the net force of these people? Is it the net force of these people? Yes, friction is also there. The answer is these are not exactly the forces applied by the individuals. Rather, they are the resultant forces. On both of them. I'll tell you why also. Because if this person pulls this person with some Newton of force, that person compulsorily should pull this person with the same force, equal and opposite, but on different bodies. That's why they do not cancel each other. This is Newton's third law. It sounds very untrue, it sounds false, but this is the fact. If you take, now though you are probably a dropper or 12th standard student, you go to some nursery school, call one kid, don't be a bully, but just call one kid and you'll be like, okay, play tug of war with me. First of all, the kid will give you very dirty looks because you are such a big person and you are, shamefully conducting an experiment with a very teeny mini person, and you ask that kid, let's play tug of war, and you pull that kid like this. And then you ask the kid, who applied more force? Kid will be like, you are a dropper student, you are 12th standard student, you applied more force, I am some chintu mintu person. But then you explain, you're like, come sit over here, take this ice cream, I'll explain you, Newton's third law. I applied 20 Newton force on you, you know what? You are also great, you also applied 20 Newton force on me. He will start scratching his head, he will be like, what the hell is he talking? But that is the fact. Both of you have applied same forces on each other, equal and opposite. If one force is action, the other force is reaction. If one force is action, the other force is reaction. Then he will ask you, then brother, how did you win? I should have lost. I should have also been, equally as strong as you if both applied same force. Then you are like, listen, I will explain you. And the explanation goes like this. See, this is our Chintu. Okay, this is you, very huge. Okay, both of you are holding hands, pulling each other out. You might be like, sir, we are applying the same force, but how come I won and this guy lost? The answer for that is, even if, let's say for example, this side you applied 20 Newton force, this guy also pulls by 20 Newton force. The friction over here is different. The grip over here is different. Maybe my grip, this guy's grip was better, maybe 40 Newton or maybe 30 Newton. And this Chintu Mintu guy had a very small grip, maybe just, 5 Newton or something. So because of which, if you just concentrate your attention on this Chintu Mintu guy, do you see 20 minus 5, 20 this side, 5 this side. So the net force is 15 Newton this side on the Chintu Mintu guy, nursery KG guy. Is that right? Everyone? Kid will slap you. Ayo, Herborine. How, man? You are so tall, no? Kid is there. He'll have to jump and slap you. Here, 30 this side, 20 this side. Do you see the net force on this big pandu is 10 Newton this side. Unbalance is there. So the reason for you winning that tug of war or you pulling that kid was not because of you applied more force. No, you applied the same force as the kid did on you. It's just that you had a better grip. You had better grip. Imagine you are standing on ice. You are standing on ice and the kid is standing on something. If you pull the kid will not be pulled. Rather, the kid will pull you towards him. Imagine you are standing on ice, slippery, wet, soapy surface. Kid is standing on the ground. Chintu Mintu kid. You pull the kid pulls you, but you will not be able to pull the kid towards you. Rather, you will move towards the kid. Are you able to visualize this? How many of you were able to visualize this? Give me a hands up or thumbs up. Yes, the kid will win. And then kid will be like, see, I won. Here, take this ice cream from my side. The kid will treat you. Cool? So this is how things work. So that is your Newton's third law, guys. So let's have a look at it over here. Let's write it down. This is the third Newton law of motion. For every action, for every action, there is a reaction. There is a reaction. They are both equal, opposite. They are equal, opposite, and on different bodies. They are equal, opposite, and on different bodies, guys. Yes, perfect. So, if I have body number 1 and body number 2, body number 1 applies a force on 2. This is force on 2 by 1. Naturally, on 1, 2 will also apply a force. This is not a relative force. Don't write, sir, F1, 2, sir, is it F1 minus F2, sir? This is not relative. This is force on 1 by 2 or force on 2 by because of 1. You can see they are on two different bodies. That's why they do not cancel. See, if it was the same body, the same force is applied on the same body, they will cancel. But they are on different bodies. How can they cancel? Got it? Yes. So I can write it down over here in simple way. F12 is negative of F21. That is the simple way of writing Newton's third law. Great. Let's do some simple questions coming up on your screen, guys. Get ready for it. Just 1 second, guys. Okay, here is the question on your screen. If mass of 0.5 kg has a velocity given by 2t cube plus 7t plus 7t, okay, meters per second, find the force on it at 3 seconds. Find the force on it at 3 seconds. That's the question. Chalo, try solving this. I'll just drink water and come. Let's do this. Velocity is given, mass is given, force is asked. As per Newton's second law, force is equal to mass into acceleration. So what I need to do is I need to find the acceleration. Acceleration is the derivative of the velocity with respect to time. That means I have to take the derivative of 2t cube plus 7t. Now what happens is 2 is the constant, just bring it outside. T cube's derivative is 3 into t raised to 2. Reduce the power by 1, take the power outside. 7, derivative of time is just 1. So therefore the acceleration will be 6t square plus 7. Now the force is mass into acceleration. So it is 0.5 multiplied by 6t square plus 7. But the question is find the force at 3 seconds. So put the value of time as 3 seconds. So 3 square plus basically 7. That's it. So you will get the answer as 3 square is basically your 9. 9 into 6, guys, is nothing but 54. 54 plus 7, guys, is nothing but 61. So it will be 0.5 multiplied by 61, which is 61 by 2, which is nothing but 30.5 Newton. So the answer will be 30.5 Newton. Very good, Satyashri, Aditi Guru, very good Madhumati, very good Paul AG, very good Rudra, very good Krishna, very good Harborine. Awesome, awesome. Very good, Pradeep. Perfect. Let's go to the next question on your screen. A body of 3 kg mass accelerates at 4 meters per second square due to an external force of 20 Newton. Find the opposing force. Find the opposing force. Opposing force like friction, or because it is moving in a air or fluid, air resistance. Some force is opposing it. So what is that opposing force? Opposing force will be opposite to the acceleration, like this. These are the forces acting on this body with this acceleration. So if somebody applies Newton's second law in the modified form, which is m into a, the net force, is it 20 Or is it this, or is it something else? Is it 20 plus this or 20 minus this? What do you think? Net force. Yep, the net force will be this and this. They are opposite. So if one is positive, the other will be negative. This will be equal to mass, which is 3, into acceleration, which is 4. Is that making sense? Okay, this is the net force. So therefore, I can just say the opposing force, if I take it on the other side, this will basically come here. So it will be 20 minus 3 multiplied by 4, which is 20 minus 12, which is basically 8 Newton. So the opposing force magnitude is just simply put 8 Newton. Very nice, guys. Awesome. Moving on to the next question on your screen. Imagine there is a body of mass 2 kg and the following forces act on it. One is, let's say, 6 Newton. Another is, let's say, 2 Newton. Another here is, let's say, 3 Newton. Another over here is, let's say, 1 Newton. These are the forces acting on the body. The question is, find the acceleration of the body. Find the acceleration of the body. Okay, chalo, let's figure this bit out. So let's take probably this direction as our x-axis, this direction as our y-axis, like this. In this particular scenario, there are different forces in different directions. I think it's best for us to find out the net force first and then solve the problem. If you notice over here, the net force will be this all added together. 6 is in the x direction, so I think I can put 6 I cap. 2 is in the negative I cap direction. 3 is downwards, so minus 3 j cap. 1 is also downwards, so minus j cap Newton. Therefore, what is the net force going to be? 6i minus 2i, that is basically 4 I cap, minus 3 minus j, that is going to be minus 4 j cap Newton. So that is going to be your net force. But we don't want to stop at that. We want to find the acceleration. So what will the acceleration be? The acceleration will be the net force divided by the mass, because force is mass into acceleration. Acceleration will be force divided by mass. So 4 I cap minus 4 j cap, whole thing divided by the mass. Mass is basically 2. 4 by 2 is 2. So it will be 2 I cap minus 2 j cap meters per second square. If you ask me what will be the direction, 2 I cap is x-axis, 2 j cap negative is downwards. So 2 I cap here, 2 j cap here. So the net acceleration will be in this particular direction. This will be in this particular direction. Somewhat in x direction, somewhat in positive and somewhat in negative y direction. I hope this is absolutely clear. And if they ask you the magnitude of it, then just take the components, square it, add it, put it in the root. So it will be 2 root 2 Newton. So that would be the magnitude of the acceleration. 2 root 2. Yes, perfect. Awesomeness, guys. Great, great, great. Proud of all of you. So these are some basic level questions on direct Newton's laws or the laws of motions, which we have just studied. Now, sometimes the question can be like this. A body of 2.6 kg maintains a velocity of 7 meters per second towards north due to the following forces. Number 1, 3 Newton east. Number 2, 1 Newton west. Number 3, maybe we can take something like 6 Newton north. and number 4 maybe 2 newtons towards south, okay, and number 5 unknown force. Question is find this unknown force. Question is to find this unknown force, as simple as that. Sir, what if mass also differs in second law, fully moving water bottle with leakage? Then that is a variable mass system. Then you will have V dm by dt term, which I showed you in the derivation over here. So this will not be 0. So the rate of change of mass will come over here. The rate of change of mass should be given to you, and that will come in the answer, and that's how you solve the problem. We see some kind of questions like that in fluid mechanics, but that is done without using this variable mass concept. We do it in a slightly different way called as the thrust force. Don't worry about it right now. In fluid mechanics, I will tell you. All right, let's do this question. Do you read this question and see that it is going with a velocity and maintains that velocity? What does this tell you? What does this line tell you, my dear students? Maintains this velocity. So you have to use the first Newton law of motion, which means all the forces together cancel out to be 0. All the forces just cancel out to be a big fat 0. And if I take the north direction like this, south over here, east over here, west over here, east taken as x-axis, north being taken as the y-axis, I can write everything in I cap, j cap and solve the problem in a very simple manner. Observe how we do this. 3 newtons east, that means this will be basically 3 I cap, 1 newton west, that means minus j cap, then 6 newton north, that means 6, sorry, this was not minus j cap, this was minus I cap, my bad, because it was west is negative I. Then north is 6 j cap, then 2 newton south, that means minus 2 j cap, south is downwards j cap, and 2 newton is the magnitude, and one more unknown force which I do not know. Together they add up to be a 0 vector. Together they add up to be a 0 vector. Perfect. So you just have to find the force, but before that let's take care of these two things. 3i minus I is nothing but 2i cap. 6j minus 2j is basically 4j cap plus that force is equal to 0. Therefore, our force will be, take these two on the other side, minus 2i cap minus 4j cap Newton. So this is the force which you will apply. It is neither in the north nor in the west, but somewhere, you know, in the different direction. So if you see, minus 2i cap will be like this, minus 4j cap probably will be like this. So our force is somewhere here. This is our force, unknown force, somewhere in the southern western region, somewhere it is like that. Is that absolutely clear, everyone? Understood? Oh, can we go ahead? Everyone till this point absolutely clear? Can we go ahead? Okay. So now that we are done with the basic questions and we have seen what the first law, the second law and the third law is, let us see the different individual forces and what they mean, and then learn about this concept called as the free body diagram. Okay. Starting off with the different types of forces, which we encounter in day-to-day life. First one being the weight. Weight of a object. Now when I say weight, do not think of, let's say I ask you your weight, you will be like, my weight is 40 kg. 40 kg is actually the mass. Weight is, what is the gravitational force acting on that body. So weight is the gravitational pull on a body. It's not the same as mass. It is a vector quantity. It always acts towards the center of the planet, or basically vertically down, So imagine you have this mass over here. This mass will experience a gravitational pull, gravitational attraction downwards. This gravitational pull only is called as the weight. And this gravitational pull will be mass into acceleration due to gravity. Acceleration due to gravity. So therefore, the weight formula becomes m into g. That is why the weight formula becomes mass times the acceleration due to gravity. Okay, so this is something which you must know. It always acts downwards. If you ask me what is the difference between weight versus mass, weight versus mass, first of all, weight is gravitational force. This is a force. This is amount of matter. This is amount of matter. That is completely different thing. This is gravitational force, guys. Second thing, this is a vector quantity. This is a scalar quantity. The unit of this is in SI unit, it is kg. In SI unit, this is in newtons. This is in newtons unit wise. Completely different things. Also, most important thing, if you travel to a different planet, if you travel to a different place somewhere, you will see your mass will remain the same. The mass will remain the same. The mass will be the same. But imagine you go to a different planet. If you travel to a different place, you will see the weight will change. The weight will basically change because the gravity at that place might be very different. In space, gravitational force is 0, so your weight will become 0, but mass won't become 0. Is that absolutely clear? Everybody with me? Yep. So another example of this, I can just tell you, imagine a person having a mass of 25 kg. The same person's weight will be 25 into g. G value is 9.8 or 10. So you can write it approximately as 250 newtons. This is in newtons, this is in kgs, this is scalar, this is vector, this is amount, this is force. If everybody has understood this concept and clear about this weight force, give me a thumbs up, then we can go ahead. Okay, fair enough. Awesome, guys. Moving on to the next kind of force. The next force is basically called as the contact force. Contact force. Imagine, something like, imagine, this is a pandu. This is a pandu. And this pandu is balancing a champa on his head. Oops. This pandu is balancing a champa on his head. So this is our beautiful champa. Okay, like this. So can we say they are in contact with each other? Yes or no? Can we say they are in contact with each other? So can I also say Pandu's head is applying some force on Champa? Champa's body is also applying some force on Pandu's head. Are these two forces equal and opposite? Yes or no? Are these two forces equal and opposite? Yes or no? Yep. Why? Because Newton's third law. Whatever force Champa applies, Pandu also applies. Equal forces, opposite direction, but on different bodies. One is on Pandu, one is on Champa. So they don't cancel each other out. Perfect. So if I see the surface of contact, maybe this is the surface of contact. This is, I'm zooming in, and maybe this is that contact area. So what will happen is, I might see Pandu on Champa's body might be applying forces like this. Teeny meeny forces will be there. Some small forces will be there. Maybe one is here, sorry, one is here, 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 one is here. Okay, like this. These are teeny meeny forces on Champa's body. This is, let's say, for example, called as the action. Then there will be reaction to it, but that reaction will be on Pandu because of Champa. So the reaction forces will be probably like this. You can see they are all teeny meeny, equal and opposite in nature. If I take the result of all these forces, if I take the resultant of all these forces together, okay, all these teeny meeny forces, Pandu on Champa might apply a force like this. Champa on Pandu, Newton's third law, will apply a force like this, equal and opposite. This C is called as the contact force. This C is called as the contact force. Any two things touching each other, the moment they touch, there is a contact force. So, I can say two surfaces touching each other, experience molecular interactions whose resultant is basically the net contact force. So if I have a body like this and it is kept on a surface like this, just like in this particular diagram, then there might be a contact force on this body, and this is represented by C. Now this contact force, actually speaking, is divided further into two components, two parts. One component is basically parallel to the surface. The other component is perpendicular to the surface. The one which is perpendicular, orthogonal, 90 degrees, normal, all mean the same thing. So that's why I call this as the normal. And the one which is parallel is often the friction, is nothing but the friction between the two surfaces. So a contact force is the sum of normal force and friction, or rather other way around, normal and friction are the components of contact force. I bet many of you would not know about this before. Okay, so normal force is the one which is the component of contact, and friction is component of contact along the surface. This is perpendicular to the surface. So that's why the magnitude of this will be just root of n square plus f square. That will be n square plus f square. That's it. Okay, something which you should know. Is that absolutely clear? Is that absolutely clear? Also remember, if the surface loses contact, if surface loses contact, then what will happen? The contact force only will be 0. Therefore, what will happen? Even the normal force will be 0, and even the frictional force will be 0. Something, an aeroplane is taking off from the runway. The moment it loses contact, what will happen? Contact force vanish. Why? Because the surfaces are no longer touching each other. So that's it. It is floating. Anything floating will not have contact force, normal or friction. As simple as that. Yep. Okay. So this is the example of your contact force. So next force coming up on your screen. Like I said before, friction will be studying it in detail in part 2. Right now we are not going to go in detail about friction. We'll be just seeing mainly questions where normal force will be there. Next is basically your tension. Lot of exam tension is there. This is basically the electromagnetic pull between the molecules of a rope or a string or even a rod, for that matter, or even a rod for that matter, when stretched, or sometimes you see the word taut. I pull it, I make it taut, I make it tight, I make it stretched. So then you will see the tension comes in. Then the tension comes in. Just let's take a simple example. Imagine this is a pandu with very, very long hands. Very, very long hands. One hand, he does not know where to keep, he's just hanging it over here. This hand is being pulled. Champa sees this hand, she falls in love with this particular hand, and Champa is holding Pandu's hand. Champa is holding this Pandu's hand. So Champa is pulling this Pandu. Champa gets attracted by this Pandu with very, very long hands, and she pulls this particular Pandu over here. So she is pulling this Pandu. So won't this Pandu's long, slender, thin hand experience tension? Definitely. Definitely Pandu's hand will experience tension. In fact, if you break it down, if you see, not physically cut it, but just at macroscopic level, you see what is happening in Pandu's hand. You will see at any particular part, you will see there will be many, many molecules. These molecules will try to go away from each other. So they will be stretched. It will feel as if they are trying to go away from each other. They are being pulled, they are being pulled, they are being pulled, they are being pulled, they are being pulled. Everywhere there is stretching which is happening. So there is tension inside. These are your electromagnetic pulls. Electromagnetic pulls which are there between the molecules. So if you consider a small section of his hand, this part will be pulled this side, this part will be pulled this side. One is action, another is reaction. That is called as the tension in that string, that rope, that rod, whatever that element is. Okay, I hope this is absolutely clear. Everyone, this is how the tension works. Ray optics, there is time for it, Shanmuga. We are going step by step. I think right now we're going to do current electricity in 12th standard NCERT. After that, we'll go to magnetism. Then I think electromagnetic waves. And then I think ray optics will come. Okay. But if you still want to know the concepts, you can always watch my JE class also on the JE English channel for concepts. It's still fine. I mean, you can watch it. Great. What about this hand? It's just lying. It's just lying. It's just lying. Do you think there is some pull? Let's neglect the weight of the Pandu's hand. Neglect the weight of the Pandu's hand. Do you think there is any pull? No, right? So there is no tension over here. No tension, no Champa to pull his hand. No tension, no problem. So no tension, that means it is basically loose. It is not tight. It is not tight or not taut. It is not taut. So then there is no tension. That means T will be 0. That means T will be 0. If you ask me what's the direction of the tension, well, see, it all depends. Well, it all depends on which part of the rope you take, which side of the rope are you examining. So actually speaking, at every point the tension acts both the ways. If you take this side, tension is this way. If you take this part, tension is this way. So basically I can say that the tension always pulls away. You can see that it always pulls away. If this is the body, it pulls away. It pulls away from the element, and is along it. What do I mean by along it? Means if this is the element, you will never ever find the tension force to be like this, or let's say like this, or let's say like this, or let's say even like this. All these are not possible, guys. So I'll just show you which and all are not possible. Like this, like this is not possible, or even for that matter like this is not possible. All these are not possible things. All these are not possible things. Not possible. Okay, keep this in mind. So it is always going to be along that element and it will always be away from that element. So it pulls it out. That is what tension is going to act like. Very good. Awesome. Now, next thing, tension is done. The next force is basically your spring force, spring or elastic force. The spring force is an elastic force, which tries to restore a deformed body. Imagine pandu. This is elastic pandu. And his friends are pulling him. Okay? His friends are pulling him like this. They are pulling him like this. So because of that, what happens, unfortunately, this pandu becomes taller. This pandu now becomes a long pandu, elongated pandu. This is a stretched pandu. Why has he become stretched? Because of the pull. On both sides. Now, in this process, this elastic pandu has changed its shape, size, right? Shape, size, everything. And imagine now these people stop pulling that pandu. Imagine they stop pulling that pandu. What will happen? This pandu will immediately start losing his height and he will start coming back to his original height. So there is a retraction, there is some kind of a restoration. So there is a restoring force on the pandu to regain his original shape and size from its deformed structure. This restoring force is like spring force, or this is how spring forces work because of the elastic forces within a body. You might have seen a spring. Have you ever seen a spring? I'm pretty sure inside a pen or maybe some mechanism or maybe those old clocks or some toys where you have to wind it and then it starts playing itself. So there is a spring. You stretch a spring, it comes back. You press up spring, it again comes back to its original shape or size. So that is what a spring force is. It is trying to bring it back to its original shape or size. And you will see it always follows a very simple rule. And the rule is that the restoring force is going to be always proportional to the amount of deformation that you produce. The amount of deformation that you produce, it is going to be directly proportional to that. This law is basically called as the Hooke's law. This is called as the Hooke's law. Hooke's law. This is called as the Hooke's law, where the restoring force is directly proportional to the deformation. But usually we don't like this proportionality. We want to write it as equality. So what do? We write it as equal to some constant into deformation. That constant is called as our elastic constant or just the spring constant Spring constant multiplied by deformation. This is basically your Hooke's law. Keep this in mind. Restoring force is spring constant multiplied by Hooke's law. Everybody clear till this point over here? No, the concepts used in NLM will be used in work power energy, rotational motion, even SHM, and even electromagnetic induction and magnetism and even electrostatics. These are the main chapters where you use this knowledge. You will see that. Cool? So it's a very, very important chapter which is used at multiple different locations. Clear till this point? Okay. So say for example, we have a spring like this. Right now it's in its natural state, natural shape and size. Let's say I extend it first and then let's say I compress it. So now this is the extended state and this would be the compressed state, like this. So if I draw a line over here, you can clearly see how much extension or how much compression is there. So this much is the extension, this much is the compression. So I'll just mark them over here. I will call that extension as X or the compression as X. Then when I'm pulling it, I have to apply a force like this. So this is a force on the spring. To compress it, I have to apply a force like this, which is FSS, stands for the spring. This spring force is spring constant into deformation. So I will say this spring force is that spring constant, usually the symbol is K, and deformation is basically X. So that's why you will see this formula, Fs is equal to K times of X. Fs is equal to K times of X. What does this spring constant depend on and what are the units of it? Everything, let's see. So this particular spring constant, unit of it, you can clearly see this is Newton, this is meter. Bring the meter down, it will become Newton per meter, number one. Next, it depends on the material which makes up the elastic body. It also depends on the shape, the size, everything. The size, the shape, everything, it depends on it. So it will be usually given to you 100 Newton per meter, 200 Newton per meter. If it is more newtons per meter, means for the same deformation, I need more newtons. So it is very stiff to elongate or compress it, very hard spring. But if it is 0.7 Newton per meter, 20, 50 Newton per meter, it is a very soft spring. I need lesser force to elongate or compress it by the same amount. So lesser Newton per meter is a soft spring, more newtons per meter is a very stiff or a very hard spring. Okay. Now, many people also might have seen this formula as negative kx. Don't have to do that, guys. That is utter waste. I'll tell you why also. See, imagine you have a spring and you basically elongate it. And this is that particular body which is pulling it. So let's say this is our x vector, which is in this way. If you show the force on the spring, versus the force on the body, they are two different things, guys. On the spring, it will be this way. Whereas on the body, if you draw the forces on the body, it will be like this. The force on the body will be like this. If this is action, this is reaction. Newton's third law. If spring pulls the body pulls the spring with equal and opposite forces on two different bodies. Here, the force on the spring, you can see, is in the same direction as that of x. So that's why this will be K into x. K into x. Here the force is opposite to x. That's why the force on the body will be negative kx. So it depends on which body are you considering. Is it the spring or is it the actual object pulling the spring? Accordingly, the sign will come. But to my knowledge and to my experience, I don't think I have ever used that because it is not needed. Why do you need that plus kx and minus kx? Don't you see, or can you not see that the spring obviously being pulled will pull back this body in this direction. So the direction is 99% known to you, or you can figure it out in the remaining 1% cases. So don't use this negative kx and plus kx. Just remember, magnitude is kx, direction I know. You tell me, are you drawing the forces on the spring or on the body? Accordingly, I will show the direction. That's what matters. Yes, I hope this is absolutely clear. Great. So we have studied all the forces now, as of now. You can see weight, which is mg. Okay, I have shown you the difference between weight and mass also. Contact force, which is the combination of normal and friction. Okay, then tension, then spring. These are the main forces that you study. There are many other forces like forces on magnets, buoyancy, viscous force, and so many other things. But right now we are limiting ourselves to only these forces in this chapter. You will study new forces as you progress ahead. Okay, so now let's go to problem solving. Now to solve problems, you need one technique which is called as the FBD, force or free body diagram. Force or free body diagram, often called as FBD. Now what is this force or free body diagram? This technique helps us to solve the problems which involve Newton's laws, and it gives you a simple set of rules which are very obvious also, and at the same time very methodical. If you follow these rules in all the problems systematically, you will be able to do most of the steps, and anything else needed from any other chapter, you will use that knowledge. So in this, what you do is, basically first step is choose a system. You choose a system. The choice of the system matters a lot. If I choose the system wrongly, I might never get the answer, or I might get the answer but in a very longer method. So choice of the system matters. Imagine there are multiple things. Okay, and maybe there is this thing over here, like this, like this. I have neglected all these things. Now this particular thing is my system. This particular thing is my system. Whatever the mass is there, that is the system. I have neglected other things for some reason. I don't know. It depends from problem to problem. Is there any technique to choose a system? Answer is no. With experience, you will get what should be my system. Just imagine the question is, I'm standing on a weighing machine. What is the reading shown by the weighing machine? Obviously, you will think about the free body diagram or FBD of the weighing machine. What forces are on the weighing machine? Because through that, you can find what is the reading shown by the weighing machine. Simply put. Okay? So, first thing is choosing the system. Second thing is basically showing all the forces on it. Showing external forces only and the effects. I have chosen this system. Show all the forces acting on it. External forces on it, not by it. By means different, on means different. I am pushing a wall. If you are drawing the forces on me, don't show the force which I am applying. Show the force which the wall applies on me, which the earth applies on me, the roof might apply on me, some magnet is pulling me, on me, not by me. So if you are considering me, show the forces acting on the system, not by the system. Also, there might be forces within the system, like my heart is pumping, okay, my hands are moving maybe, and there are some internal muscular forces. Don't show these muscular forces or heart pumping forces or other things. Internal forces, don't worry. Outside forces, only worry. Cool? So, show only the external forces. Maybe this object is applying a force like this. Maybe this triangle is maybe pulling it. Maybe this body is pulling it like that. Maybe this is pushing it like this. Show the forces acting on it. And the effects. Effects means, what does it do? How is it affected? It's affected, and that's why it is moving in this direction. It is accelerating in this direction. So show the acceleration of that system. If you don't know it, assume in some random direction. If you know it, show it in that direction. Okay? At least the direction part is very easy most of the times. Once you do that, the third step is resolve the forces in suitable axis and direction. Meaning, once you have had this particular body, somebody might say, listen, this is my x direction, this is my y direction. Okay, this is x axis, this is y axis. Show everything as components. So whatever force was like this, 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 split it up into components. Maybe one component here, 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 one component here. Even the accelerations might not be in the same direction, so you might have to even split the accelerations into two directions. Depends from problem to problem how you have chosen the axis. So do all these things. The last step is to apply Newton's laws. Okay, apply basically first or basically the second Newton's law of motion according to the problem, meaning all you do is net force in the x direction will be the mass into acceleration in the x direction. Think about it. Similarly, net force in the y direction will be the mass times your acceleration in the respective directions. That's all. F is equal to ma. F is equal to ma. When I say net force, so some forces are this way, some forces are this way, that way. You find the net force in x, it will be mass into acceleration in the x. Then net force in y, all the vertical directions, you add them up. Finally, the net force will give you mass into acceleration in the y direction. That's what you use. And solve the question to get the answers. That's all you need to do. Okay? Everybody fine till this point? Everybody fine till this point? Very simple steps, guys. Some 4-5 steps only. That's all. After this, you just solve them. Fifth step is solve. You will be like, sir, I did this. What to do next? You didn't tell me. Solve, guys. Obviously, you will solve the equations. Okay? Simple. So let's start doing the questions, guys, one by one. We'll start off with a symbol free body diagram and then we'll slowly complicate it. If by chance you have to apply first law, means all these accelerations will be zero. So for equilibrium, when a body is in equilibrium, what is the meaning of equilibrium? For equilibrium, you will see all the accelerations will be zero. That means you can indirectly say that the net force in the x direction is zero or the net force in the y direction is zero. The forces are balancing each other. They are basically balanced forces. They are basically balanced forces. Balanced forces. Correct. They are basically balanced forces. Very nice. Very nice. Awesome. Let's do some questions. Let's start with a very simple example and slowly we are going to complicate it and see different kinds of questions. Okay? Chalo, let's do this. Yep. A simple block on a ground surface. A simple block on a ground surface. The different forces on it, all the values, everything I want to find. So the common theme is every time I will show the forces, I will resolve it, I will solve it and find all the unknowns, whatever is required, acceleration, etc. In this particular problem, what I can see, there are two objects. One is the mass or that box and the earth. I want to find out about the box, so obviously I will show the free body diagram of the box. So I will just draw the box over here. I'll just draw the box over here separately. And then let's think what are the different forces acting on the box. I'll ask the box, box, what are you experiencing? Box will be like, earth is pulling me. Where is earth pulling me? Down. What is the force with which the earth is pulling me? Down. M into G. M into G. Next, box, any other force? Box will think, yes, I am resting on that ground. That ground is helping me, it is supporting me, it is holding me. So it is applying a normal force at the point of contact over here. This weight was pulling me down. There is a normal force acting on the bottom surface. Anything else? Box will be like, nothing. What are you doing, box? What is your effect? Box will be like, I am doing nothing. I am eating 5-star and doing nothing. So box will say, I am at rest. If I am at rest, what will you do? Guys, if at rest, first law, equilibrium, net forces will be 0. That's all. Oh, do I have to split any forces? Nothing. Everything is in the vertical direction. What will you split? Nothing is there to split. So you will just say, okay, normal minus the weight will be 0, or normal is equal to the weight, which means normal is equal to mg. Perfect. Done, dusted, solved. Very nice. Now, I have asked this question to many people and they give wrong answers also. I have asked, if weight is considered the action, where is the reaction to it by Newton's third law? Where is the reaction to it by Newton's third law? And many people say, sir, this is the reaction. But I don't think so. I don't think the reaction is this. I'll tell you why. If you go back to Newton's third law, where did it go? Yes. F12 is F21. If this is gravity, this is also gravity. If this is magnetic, this is also magnetic. If this is electrostatic, this is also electrostatic. If this is nuclear, this is also nuclear. It can never happen, this is magnetic, this is electromagnetic. This is gravity, this is nuclear. No, they have to be of same kind and opposite directions. And because this is there, this is there. So think about it over here. How is it even possible that weight, which is gravity, is action, and you say normal, which is not gravitational force, is the reaction? So it can't be true. So normal is not the reaction to the weight. Normal is not the reaction to the weight, mind it. In fact, if you draw the free body diagram of the earth, which you rarely draw, but just for the problem's sake, if you draw the free body diagram of the earth, then you will ask, mass, who pulled you? Earth pulled me, sir. Earth pulled me down. So I'll be like, hey, you don't know Newton's third law? You also pull the earth. So you will pull the earth by the same force, mg force. So on the earth, the box will pull it. Think of it in a very weird manner. The box on the earth is the same as the earth on the box. Just because you're standing here, nothing like that, just think of it this way. There's nothing like I can stand here also, no, just imagine there is a person standing like this on the earth. If you see from his perspective, the earth is on him or he is on the earth. One and the same thing. One and the same thing, right? Are you able to visualize this? So you should be proud of yourselves that you are making the earth, stand on you. You are pulling the earth with the same force, no cheating, as the force which the earth pulls you. You are pulling the earth with the same force as with which the earth pulls you back. Yep. So therefore, the earth experiences mg over here, and that is the reason why this becomes your reaction. This becomes your reaction, mg. Is it clear, everyone? Not just that. If I ask you, wait a minute, then normal is not reaction. Yes, it is not reaction. I can take anything as action, guys. I can say this is action, this is reaction. Action, reaction is my definition. You can choose anything as action, other thing will be reaction. Now, if I take this normal as the action force, you'll be like, where is the reaction? If it is n, symbolically the reaction should be also n only, but it will be on the different body. I will ask the mass, who applied normal on you? Box will say, earth was helping me, supporting me. So you also do the same thing, Newton's third law, but push him in the opposite direction, that's all. So on the earth, the normal force will be like this. The box will be pushing it down like this. So this is the normal force on it. So this is the reaction. Is this absolutely clear? How this simple problem had so many hidden concepts. Very good, Divya, Riru, Krishna, awesome, Rudra, Madhumati, very good, Aditi Guru. Keep the chat flowing, keep learning, keep liking, keep subscribing. If you have not yet done all those things, please do that. Great. Let's go to the next question on your screen now. Now what happens is, we keep a block on another block. We keep a block on another block. Let's say this is 2 kg. Let's say this is 5 kg mass. And this entire thing is on a surface at rest. Question is drawing the free body diagram, etc. Let's start it one by one, starting off with the upper mass and then the lower mass. Okay, let's do it one by one. So let's take the 2 kg mass, then let's take the 5 kg mass over here. Okay, let's ask 2 kg mass. 2 kg mass, 2 kg mass, what are the forces acting on you? 2 kg mass is like earth is pulling me down. Okay, show the basic forces first. Earth is pulling you down. How much force? mg. What is your mass? 2. What is the acceleration due to gravity? G. So 2g. 5 kg mass, 5 kg mass, any other force? Yes. Weight. Earth is pulling me down. Okay. Show the basic forces first. We'll go to other forces later on. So it will be nothing but 5 into g. It will be nothing but 5 into g. Any other forces? Yes, of course. 2 kg mass will say, listen, I am standing on 5 kg. I am pushing 5 kg down. 5 kg is pushing me up. So there is a normal force on me. So I'll call it N2. I will call it N2. Normal force on the 2 kg block. Normal force on the 2 kg block. I can call it N2, N1, N3, whatever you want to call. I'll call it N1. Doesn't matter, guys. Any symbol you want, you can use. You can call it R1 also. Sometimes normal reaction they call it. So that is also fine. Next, you will think, on 5 kg mass, any other force? Yeah, it is on the ground. So the ground is being pushed down, ground will push it up. So the ground will apply a force on this, I will call it N2. But there is one more thing. This 5 kg is below 2 kg, 2 kg is pushing it down. So should I show 2g down like this? 2 kg block is pushing 5 kg block down like this. So should I show 2g force down like this? No or yes? Think about it. No or yes? Think about it. Thank you for all the love and hearts and the celebrations. Thank you so much, guys. The answer is no. I'm like, why, sir? But the 2 kg block is on the top of it. So shouldn't 2g act down? The answer is no. Why? Because 2g, who is applying? On whom? Earth is pulling 2 kg mass down. How can you show 2g on 5? Wrong, guys. Weight acts on that respective body. My mass is 2 kg, I will experience 2g. My mass is 5 kg, I will experience 5g. My mass is not 2 kg, why will I experience 2g force? Rather, what I experience is the normal forces reaction. So it will be N1 over here. In fact, this is action, this is reaction. 5 held 2. So 2 pushes 5 with same opposite forces on 2 different bodies by Newton's third law. So a lot of people make a mistake here. They show 2g, which is not the same. Which is not the same. Yes, the value of N1 is 2g, but does not mean N1 is 2g. There is a difference between equal to something is equal to something and saying something is something. Imagine today Krishna and Tanuja. Hi Tanuja. Both of them score 700 marks out of 720 in NEET. Krishna's marks 700. Tanuja's marks 700. So Krishna is equal to Tanuja. They both will be like, no, sir, we are different people, sir. So there is a difference between saying Krishna is Tanuja or Tanuja is Krishna and Krishna's marks is equal to Tanuja's marks. Getting my point? So the normal forces value will be 2g, but it is not 2g. Get the difference. Yes, both of them are at rest, of course. This is also at rest. This is also at rest. And when things are at rest, we know what to do. Balance the forces. Balance the forces. So N1 will be 2g. N1 will be 2g. Or rather, you can think of it like this also. N1 minus 2g is 0. Therefore, N1 is equal to 2g. Here, upward force is N2. Downward forces will be balanced by it N1 plus 5g. But N1 is 2g. But N1's value is 2g, so it will be 7g. So that is the value of N2. Is this clear, everyone? Very good. Awesomeness. let's go to the next question. Imagine there is a 3 kg block and another 5 kg block, and they both are on a smooth surface like this. And then what happens is somebody is pushing these blocks from here and somebody is also pushing these blocks from here. This person pushing these blocks is applying, let's say, 20 Newton force. This person pushing over here is applying, let's say, 4 Newton force, like this. And you have to find everything. Is it accelerating? Is there forces between them? What are the forces of interaction between them? Everything. Okay, so let's try to solve the problem. Now, first of all, if you see each block separately, like this, this is our 3 kg block, this is our 5 kg block, and you ask these blocks, what are the forces acting on you? These blocks will reply immediately, Earth is pulling me down, sir. Okay, so 3g down, 5g down. Okay, 3g down, 5g down. Perfect. Any other forces? Yes, sir. Obviously 20 Newton is applied on this and 4 Newton chintu mintu force applied on 5. Any other force? Yes. They are resting on the ground. So ground is applying a normal on the 3 kg block and the ground is applying a normal on the 5 kg block. Any other force? Yes. 3 kg pushes 5 kg, 5 kg pushes 3 kg. So 3 kg pushes 5 kg like this. Don't show like this on 3 kg because what 3 kg does is never shown. Never show the forces by the body, always show the forces on the body. Is that right? On that body. So 3 kg applies a push on 5 kg. 5 kg in turn reacts by Newton's third law and applies the same force in this direction. These are the forces, but always remember I have given you all the steps right over here. Also show the effects, which is the acceleration before splitting and doing other things. So effect meaning acceleration. Won't this entire thing move because the forces are not balanced? They will move. So if this moves by some acceleration, will this move by the same acceleration or more acceleration or same less acceleration? Same, more or less? What do you guys say? Come on, put it up in the chat box, everyone. All the warrior pandus. What do you think? These blocks will move together. If 3 moves 1 centimeter, 5 will also move 1 centimeter. If this moves with 5 meters per second, this will also move with 5 meters per second because they have to cover the same distances. They are touching each other. So if this has an acceleration of 7, this will also have 7. So they should have the same acceleration. Now let's use Newton's laws. Now let's use Newton's laws to solve the problem, but there is a small hindrance. Sir, I don't know this P, sir. Sir, I don't know this A also, sir. Can I solve that problem? Yep. That's where the choice of the system plays a very important role, as I told you in this starting part only, of FBD drawing. I told you right over here. Choosing a system plays a very, very important role. So just imagine, instead of 3 and 5, had I chosen 3 plus 5, had I chosen 3 plus 5 as a system, 3 plus 5 is basically 8 kg as a system. Then the forces acting on it are basically, one is the 20 Newton force, the other is that 4 Newton force. There will be a total normal on it and there will be a total weight of it, which is basically 8g. And this whole system will accelerate with some amount. Now I think I can solve the problem because this push between them will become what? This push between these blocks will become internal force. So I don't bother about it. I don't care about it. So internal forces never ever bother. So what will I do? I will say net force is mass into acceleration. Net force is mass into acceleration. Everything is horizontal. This force is in the direction of the acceleration, so I'll put 20. This force is opposing it, so minus 4 is equal to mass, which is 8, times the acceleration, which I do not know. Therefore, 16 is equal to 8 times of A. Therefore, acceleration is 2 meters per second square. Perfect. I got the acceleration. I will use it. I will use it. I will use it over here. I will use it over here. I can say again, net force is mass into acceleration. Acceleration is right, so I can use it over here. 20 minus P, 20 is in the direction, P is opposite, is equal to mass times acceleration was 2. So therefore, P will be 20 minus 6, which is 14 Newton. So the push is 14 Newton. Everybody with me? Yep. You will be like, sir, what is the use of this? No use. I already found P. I already found P. There is no use of that. But if I write it, I can verify whether my answer is correct or wrong. Yes, I can use it as a verification step. Check this out. Push is in the acceleration direction. 4 is opposite, is equal to mass times the acceleration. Acceleration I can substitute over here, which is 2, and push is nothing but 14. 14 minus 4 is 10. 5 2s are 10. Yes, it is correct, whatever we have done. It's just for verification, otherwise I don't need it. Awesomeness. So this is how you do these block questions. Let's go to the next question coming up on your screen. Imagine a single block. Imagine a single block is over here. This is angle theta, this is mass m, and I want to find what is the acceleration, what is the normal, etc. Okay, so let's try to solve this particular question. A block on an inclined plane. Start off by drawing the forces on it. Obviously, one of the forces is mg. The other force is the normal force on it. Normal is always perpendicular. This is a smooth surface, so the normal force will be like this. The block will slide down. If I keep this block, it will start sliding down. Zoop. So it will definitely have some acceleration down the plane. I know the direction also. Now here is the first time you are seeing the forces are at an angle, and the choice of the directions play an important role. I have a feeling it's better to take down the direction as x-axis, up the plane as y-axis, because it is tilted. Tilted diagrams always use this direction as your x-axis and this direction as your y-axis. The moment you do that, you will see acceleration is along x, normal is along y. It's only this mg who is the culprit, who is at a very weird direction. Now you will be like, okay sir, I have to split mg then. Of course you have to split mg into two components. One component is readily seen, it will be like this. The other component will be like this. But the problem is this mg cos or mg sin? So for that, I use a trick which I have told many of you before also. If you have an inclined plane making some angle theta and your body is somewhere over here, what you do first is, okay, you have the inclined plane, you drop a perpendicular to that inclined plane. You also consider a horizontal line and also consider a vertical line. Show these lines first. How many parts you are divided it into? Count it. 1, 2, 3, 4, 5, 6, 7, 8. So this is your trick method where you divide by 8 parts. Divide by 8 parts trick. Very simple guys. See, if this angle is theta, naturally even this angle will be theta. This will be theta, right? If this is theta, same theta will be here. Then leave a part, go to the next, leave a part, go to the next, leave a part, go to the next. All these will be theta. All these alternate angles will be theta. Very simple. Yes. So, if you go back over here, the same thing can be applied, and you will see over here also, this will be like horizontal, this will be like vertical, okay, something like this. This is your division by 8 method. Okay, you will see that this will be theta, leave that, this will be theta, leave that, this will be theta, leave that, this will be theta. So the one which is closer to theta is always the cos, C for close, C for cos. So that's why this will be mg cos theta, closer. This component is far away, so that's why mg sin theta, mg sin theta. Is that clear, everyone? Okay, perfect. So now you just apply Newton's laws in different directions, especially starting off with y-axis first, and then let's go to x-axis. In the y direction, can you notice there is no acceleration only? Acceleration is only in the down the inclined plane, which is x, nothing in the y. So actually speaking, normal minus mg cos is actually mass into 0, nothing in the y direction. Therefore, normal is actually mg cos theta. But in the x direction, there is only one force, which is mg sin theta, is equal to mass into acceleration, which is a. Therefore, mm cancels and you will get acceleration as g sin theta. So that's the acceleration, that's the normal acting on it. Is it clear, everyone? Shall we go ahead? Shall we go ahead, everyone? Okay, perfect, perfect, awesome. Let's go. So this trick we have learned. We have seen this block on block questions or block with block questions like this. Now, slowly, let's move on to the next type of questions where you will have tension. Now, if you take a string, hang a mass of, let's say, 2 kg, and then hang another mass, let's say 3 kg. This is that roof. These strings will be under tension. We have to find the tension in these strings. So let's do this slowly. Okay, we have to do this very, very coolly, or else you will make some small directional mistakes and even calculation mistakes. I want to find the tensions in all these strings, drawing the free body diagram. Okay. What I will do, if I want to find the tension in this string, and this string, I will take 2 and 3 kg blocks separately. See what are the forces acting on them. Okay, so this is our 2 kg block. This is our 3 kg block. Fair enough. This is 3 kg block. This is 2 kg block. I'll ask the 2 kg block, what are the forces acting on you? 2 kg block will say, earth is pulling me down. Okay, I will show 2g force down. 3 kg block will also say, me also, earth is pulling me down, like one complaint box. Okay. Anything else? Yes. Tension will be there. Now you'll be like, where will be the tension? Let's think. See, this rope will pull this block up. Why? The block is pulling the rope down. The rope will pull the block up. The rope is holding the block. So think of it like this, as if a small part or that knot where it has been tied is also a part of the system. So tension always acts away from the body. That's what I have been telling you. Tension can never push a body, it can only pull things. So this rope can only pull the body which is hanging below it. So the tension will be upwards like this. Same way, this rope below it will also pull that 2 kg down, because this weight indirectly transfers its force to the 2 kg. So there must be another force of T2 down over here. Because of this string will pull the 2 kg block down. String always pulls, or it's always away from the body. So you can see it's away from the body. Same string is connected to 3 kg. So the same tension will propagate over here. So that's why this 3 kg will also experience the same force upwards. It is again pulling this 3 kg up. 3 kg or else will fall down. So the string is like, I will hold you, I'll support you. As a result of all of this, what was happening? This was at rest, even this was at rest. Perfect. So what can I say now? Here I can say the upward force should balance the downward force. So T1 is equal to 2g plus T2. Here I can say T2 will be 3g. Put the value of T2 over here, which is 3g. This is 2g. So therefore, how much is T1? It is basically 5g. It is basically 50 Newton. This is basically 30 Newton. Is it absolutely clear how we found the force of tensions in both of them? Great. Next. There is a rope like this, ideal rope. Somebody is applying 30 Newton here. Somebody else is applying 30 Newton here. Can you find the tension in the rope? Can you find the tension in the rope? I'll give you the options also. 30 Newton, 15 Newton, 60 Newton, 0 Newton. What do you think is the correct answer to this? All right, here we go. Many of you might think it is 0, but it is not 0. Very good, Krishna knows it already. But it is not 0, guys. The correct answer to this question is 30 Newton. You might be thinking what the hell just happened, but it is true. I'll tell you very simply. If you just consider the left half or the right half or the left part or the right part of that rope, it will look like this versus like this. If you show the forces on them, this side 30, this 30. Do not forget that they are at rest. If they are at rest, net forces should be 0. So if there is some tension here and some tension here, don't you see 30 newtons will be the tension force? Tension will be 30, tension will be 30. I know you thought that, sir, but I was pulling equally, so all the forces cancelled. See, there is a difference in net force being 0 and forces being not there at all. When force only is not there, 30 is not there, 30 also is not there. Nobody is pulling. It is loose. Tension will also be 0. But forces are there. You are pulling, I am pulling. 100% there will be tension. Tell me one thing. If instead of this diagram, imagine there was a wall over here. Imagine there was a wall over here. Okay, something like this. This continues. And this rope was embedded in it. And there was a pandu. You know, there was a pandu over here who is pulling this particular rope. Who is pulling this particular rope. Then you will be like, sir, because you are pulling it with some 30 Newton force, hence the tension is also 30 Newton in the rope. But don't you forget that even the wall also resists the rope, or else the person with the rope will fly off and there will be a force by the wall of 30 Newton. There will be a force by the wall and it will be of 30 Newton magnitude. Exactly. So, just because I never showed this does not mean it was not there. Just because you close your eyes does not mean the walls are not there. The walls are still there. It's just that you did not see it. Same way, think of this as a support. Think of this like a wall and you are pulling it. So obviously the tension will be 30 Newton. Just because you did not see it does not mean it is not there. It will be held over here. That is the answer. Is that clear, everyone? Guys, please maintain decency in the chats. Don't go into spam, then you will get blocked by the admin. Be careful. Okay, perfect, perfect. So let's go to the next kind of question coming up on your screen. Imagine there is a block, another block, and somebody is pulling it with some force F, this is M, this is 3M, this is 2M. It's all on a smooth surface. There is tension T1 here, there is tension T2 here. Question is to find T1 and T2. It's like an engine pulling the bogies of different masses. Each bogie will pull the next bogie or the next crate or the next compartment with some different force. You have to find these forces. Let's see how to do this. Now, again, this T1 and T2, if I have to find, obviously I have to draw the FBD of these masses individually. But when I show the FBDs, I realize one thing. Acceleration will be needed and I do not know the acceleration. So what I will do first is I will take the entire thing as a system and try and solve it, and then we will go ahead. So once acceleration is found, then we'll go ahead. So let's take the entire thing as our system, guys, and this entire thing as a system has a mass of nothing but 6m. The forces on it is only one force, which is F. So there will be acceleration like this, acceleration like this. So if I use F is equal to ma, F is equal to 6m into a. Therefore, acceleration will be F by 6 times of m. So I know the acceleration is F by 6m. Okay, fair enough. Now let's consider each of these blocks separately. Let's say I take 2m mass separate. Let's say I take 3m separate. And let's say I take m separate. Okay, m separate. So 3 masses, m, 3m, 2m. Let's show the forces on each one of them. Usual forces, weight, 2 mg, 3 mg, and mg. Normal is also there. Let's say n1, let's say n2, let's say n3. All the usual forces. Apart from that, this force I have applied on m, so it has to be shown. This string will always pull the objects. Never can a string push. So this string will always pull with a tension of T2. Always tension acts away from the body, so show it away. Tension acts away from the body, so show it away. Same story repeats for T1. T1 pulls the bodies, so show T1 here, show the T1 over here. And the result of all of them is the acceleration. Acceleration. Same acceleration for all of them. This is the complete FBD. Just cross check it. Once done, write the equations. In which direction? Obviously horizontal. Okay. Who will I select? Or should I do it for all? I think let's do it for this. It looks easy. There's only one force over here. So I can see T1 is equal to mass times the acceleration. The acceleration value, I got it over there. What was the acceleration value which I got it? It was F by 6 times of m. Perfect. So mm cancels, 2 and 6 becomes 1 by 3. So the tension will be F by 3. Perfect. So I got that first tension over here. I think I can solve it for this guy and find T2. I don't think I need this. Without this also I can do this. How? In this case it is going right. So F will be the positive force. Minus, why? Because T2 is opposite to the acceleration. Minus T2 is equal to mass times the acceleration. Okay. So what is the acceleration value? Acceleration value is F by 6m. mm cancels, it will become F by 6. So therefore, this is F minus T2. Therefore, T2 will be, bring it on the other side, bring this here. F minus mm cancels, so F by 6. So therefore, T2 will be basically 5 by 6 times of F. 5 by 6 times of F. Perfect. If at all you do it by using this also, you will get the same answer. Just that now the equation will be T2 minus T1 will be 3m multiplied by that acceleration which you found out, which is F by 6m. That's it. If you do it for this. If you solve it, you will exactly get the same answers. Cool? This is how you do those problems where the ropes are connected one after the other. Great. Cool. So we'll do one thing. We'll take a short break. We'll take a short break, guys, in Newton's laws of motion, and then we'll return. Okay? We'll just take a short break and then we'll continue with these problems. Just take a short break. In 15 minutes, we'll take a break. Welcome back, everyone. Good afternoon again. Yes, time to continue our classes. Yes, your Captain Shreyas Sir is back. So before the break, we have seen till tension and we have seen couple of problems. Let's just do one more problem. Can I get rid of this? I don't want this. Okay, thank God it went. Okay. Yeah, let's do one more interesting question where, see, in all these problems, the tension was same throughout the string and the string was ideal. The string was basically ideal. This question, you will see the string is non-ideal string, meaning, look at this. There is a rope, there is a mass over here, let's say it is 3 kg. This rope has a length of, example, 4 meters, and this rope has a mass of, example, 2 kg. The rope itself has a mass. Now what will happen is, because the rope has a mass, the tension will be different at different points. Tension no longer will be the same. If this was massless, tension everywhere will be 3G, which is 30 Newton. So you need to be careful where the problems involve ropes with masses. How do we solve this particular question? Well, first what I will do, I'll understand that, okay, the tension is different. I have to find the tension as a, probably a function or a relation with where you are. So first let's decide where you want to find the tension. So maybe it is somewhere over here and that particular point is at a distance x from the bottom. Is at a distance x particularly from the bottom. Okay. So what I will do, I will take this entire thing as a system. This x plus this 3 kg, this joint which is there, it will become an internal force. At this point, I have just imagined a cut. So it will look something like this. This is that rope, this is that rope, and this is that particular block. This is 3 kg, and this is that string which has been considered of x amount only. That's it. That's my system. Now the forces on that system are as follows. This part will experience a tension. Tension always pulls away from the body. Obviously the upper part of the rope will hold the lower part. That's why the force is upwards. Very clear about this? Yes. Hello Shruti, hello Vishwanathan. Most of the physics, Vishwanathan, will be taught by me. Yeah, you will have our amazing teachers as well, other master teachers who have been training and guiding it for very, very long time and with lots of experience when producing results. So only those kind of teachers will be there who are either themselves from IITs, right? So you will have some teachers along with the main teachers from YouTube, and those other teachers are already teaching in other batches in our Vedantu platform. Okay, so that's how it works. All right. Apart from that, I think there will be a 3G force down, and the result of all of them will be that it is at rest. Okay. There is one more thing. There is this much rope that will have some mass. So there will be an additional weight of that particular rope. So it will be mass of that rope into G, which I do not know yet. This is that part of that rope. This much mass is Mr into G. Now you will be like, sir, what is this mass of that rope? It won't be obviously 2 kg. Why it won't be 2 kg? Because 2 kg is the entire rope's mass. So this much part will have some different mass. One thing is clear though. One thing is clear. If I take small sections of the rope, per meter, the mass will be same. In fact, I can just say the mass per unit length will be the same everywhere. So if I take the entire rope, the mass is 2 kg, the length is 4 meter. Or if I take this much, it is mass Mr and the length is basically x. So mass per unit length is going to be the same. Looking at this, it is very obvious that this MR 2 by 4 is as it is into x, so it is basically x by 2. So MR is basically x by 2 kgs. So instead of MR, I can just put it over here. I can just put it over here as x by 2. This x by 2 just came from this logic over here. This logic over here. The mass of the rope, which is just over here, x by 2 kg. Perfect. So now we can solve the problem, my dear students. Net upward force should be balanced by the net downward force. So 3g plus x by 2 g. So you can take g common. So it will be 3 plus x by 2 whole thing into g. So that is the answer. You can see the tension will change with x. Tension is not the same everywhere. So keep this in mind. When ropes have masses, when ropes have mass, you will see the tension usually will not be constant. The tension usually will not be constant. Okay, so keep that in mind. Very, very important. Yep. Sukanya, no, like I said at the beginning only, this is just the part 1. We'll do part 2, where we'll be doing some friction problems, block problems, and even the some parts which we'll be leaving today. Right. We'll be doing it in 2 parts because Newton's laws is a very big chapter along with friction. So in some books, Newton's laws and friction are 2 separate chapters, you will see, especially H.C. Verma. Alright, let's do another amazing question, guys, coming up on your screen, where you have multiple strings joined at the same point. This is also a very famous kind of problem where you have something like this, maybe like this, and then there will be some mass attached over here. And maybe this is given to be 60 degree, this is given to be 30 degree, example. Or you can take any other angles also, it's up to you. Okay. Now the question is, these 2 strings which are being supported by the ceiling are holding this mass together. What are the tensions in these 2 strings? How do we solve these kind of questions? Okay, how do we solve these kind of questions? So first of all, in these questions, wherever 2 or 3 strings are joined together at a single point, what you should do is show only the FBD of that particular point or around that particular point. That junction, that node, that point which is knotted, just show only the forces on that particular section. What you will see is there will be a tension like this. This point will be pulled by this string like this. Always observe it like this. This element is here, this section, and this section. So you will see there will be one force which is like this. Let's say we call it T1. Another force by this string over here, that will be again pulling it away. So that would be T2. And this mass will be pulling that node downwards like this with a force of mg. The weight which is there will be transmitted via the string over here. It will be pulling down with mg force. These are the only 3 forces. I can see this junction will be at rest. So obviously all the forces must cancel each other. But even before that, let's split the forces which are at an angle. Whenever forces are at an angle, split the forces. That's what you will do. So this tension will have one component here, another component here. This tension will have one component here, another component over here. Like we already have seen, this is 60 degrees, this is 30 degrees. So we know what those components are. This will be T1 cos 60, which is T1 by 2, This will be T1 sin 60, which is T1 root 3 by 2. This is T2 sin 30, which is T2 by 2. And this is T2 cos 30, which is T2 times root 3 divided by 2. These are the components of those forces. Obviously, since it is at rest, all the forces must cancel each other out. So let's start by horizontal direction first. So in the horizontal direction, which is in the x-axis, T1 cos 60, which is basically T1 by 2, which is towards the right side, will be balanced by this force towards the left side. There is nothing else in the horizontal direction. Other components are vertical only. 2 cancels. Therefore, T1 will be basically T2 times of root 3. I will not get any value from here, but it's just a relationship. I don't know if I'll use it later on or not. Let's just keep it on the sides. Okay. Let's write the equation in the y direction. In the y direction, if you notice, these two forces are acting up, mg is acting down. Upward forces are T2 by 2 plus this is T1 times root 3 by 2. This is equal to m into g. Perfect. 2 goes up. So it will become T2 plus T1 root 3 is basically 2 times of mg. But wait a minute. T1 is T2 times root 3. Okay. So how about substituting T1 as T2 times root 3. This root 3 is as it is equal to 2 times of mg. Therefore, T2 plus 3 times T2 is equal to 2 mg. Therefore, 4 times T2, 4 times of T2 is equal to 2 mg divided by 2. So it will become 2 times T2 is equal to mg, or rather T2 is nothing but mg divided by 2. Perfect. I got the value of T2. Substitute it over here. So mg by 2 and root 3, that is the value of T1. So I have got tension 1 and tension 2 both. So showing the forces, resolving it, balancing it, solving it. All the same steps what I have been telling you in FVD. Yep. Perfect. Is this clear how to solve these joint related questions? This is how you solve this joint related problems. So I've seen tension related, normal related, and blocks and inclined plane related questions as of now. Let's do next type of question. Let's do next type of question which are related to basically springs. Okay. Let's do some spring related questions. Imagine there is a spring like this which is attached on the ceiling, and it has a spring constant of 200 Newton per meter, and this is basically 4 kg. Question is, at equilibrium, what is the extension? At equilibrium, what do you think is the extension of that particular spring? So what will happen is, once this system is released, it will settle down eventually. The spring will be elongated and this mass will definitely come down somewhere over here. The spring I am not interested in so much, nor am I interested in this particular ceiling. I am just interested in this block of mass 4 kg. On that block, because the mass has come down by some amount, there will be, I think, only 2 forces. One is its own weight, which is 4g, and the other is the spring, which will pull it back. Because the spring gets extended on the body, it will pull it back. Think about it. It will pull it back. By how much force? Kx force. Will I put minus kx or plus kx? I will not think about it. It is understood that it will be opposite to the extension. Obviously, the block is pulling it down. The spring will pull it up. Spring is holding it. It is supporting it. So it's up. And the result of all of them is that it is at rest. So obviously, all the forces must be balanced. So therefore, kx will be equal to 4 times of g. K value is 200 into x is basically 4 into g, which is basically 10. 0, 0 cancels. So x will be 4 divided by 20, which is nothing but 1 by 5 of a meter, which you can also write it as 100 by 5 of a meter, centimeter, which is nothing but 20 centimeters. 20 centimeters or 1 by 5 of a meter. That is the answer. Is that clear, everyone? How you solve this? Okay. So this is a simple problem involving a single spring, but we'll do some more questions. Don't worry. So let's go to the next question. Here it is. Okay, this is the diagram, and the question is find the acceleration. The question is find number 1 acceleration of 2 kg, number 2 the spring force, which is involved over here. It's a very beautiful question. This kind of question also you will see very commonly asked in many papers. Now in this question, what happens is, if you notice, there is a single spring, 2 blocks. Blocks are free to move independent of each other because the spring can stretch. It's not like if this goes 4, this also has to go with 4 meters per second square. No, this is not a string, this is a spring. If it was a rope, if 3 kg goes some meters per second square, 2 had to go that much. But here there is no such obligation or some rule or some compulsion over here. Okay. So let's think, how do we solve this question? Maybe I have to draw the free body diagram separately. So here is what I will do. Oops, sorry. I will draw first the free body diagram of 3 kg because I feel a lot of information is given over here, and maybe then slowly I will move to the other mass. Then maybe I will move to the 2 kg mass. So 2 kg mass I will draw it later, 3 kg first I will do it. Usual forces, weight, obviously normal is also there on the 3 kg mass. I am not interested so much in the vertical, maybe in the horizontal things will matter. This force is nothing but 16 Newton. Okay, 16 Newton is there. What else? This spring will also apply some force. In fact, if you notice, the acceleration is 4 meters per second square. So the net force is being created. You might say, sir, isn't 16 is equal to mass into acceleration? In fact, it is not. 3 4s are 12. This is 16. So obviously they are not equal. So there must be some spring force involved. If I show that the spring force is like this, then my FBD is complete. I can say 16 is in the direction of acceleration. This spring force is opposite to it. So Fs is equal to mass multiplied by acceleration. Therefore, the spring force will be, take it over here, take this over here, 16 minus 3 into 4, 3 4s are 12, 16 minus 12 is basically 4 Newton. So the spring force is 4 Newton, which we have solved the second part of the question. How much is the spring force? Now that same spring force will continue throughout the spring and it will reach here. So on the 2 kg, the spring force will be here. Equal, opposite, Newton's third law also. The same spring force always tries to, continue throughout the coil. So if the spring is pulling this 3 kg mass this way, the same spring will push the other mass this way. If it was pushing this mass that way, then it will also push this mass on the left hand side. Understand that? So either it will pull together or it will push at the same time. So 100% it is this way. I won't show spring force the other way around. Okay, I hope that logic is clear. This is 20 Newton. Now the value of the spring force came out to be 4 Newton. Obviously 4 is much smaller as compared to 20. So hence the acceleration must be towards the left hand side. So equation wise, 20 minus 4 is mass times acceleration. So therefore 16 is equal to 2a. Therefore acceleration is 8 meters per second square towards the left side. So we have solved the first part of the question also. Is this clear, my dear students? Spring force 4 and acceleration of the other mass as 8 meters per second square. Beautiful, amazing question, right? Great. Let's go to the next question, guys, coming up on your screen. Here it is. There is a spring. One person is applying a force of 30 Newton here. Here also 30 Newton. Spring constant 100 Newton per meter. Question is, find the extension in the spring. Find the extension in the spring. Come on, my dear students. How much is the extension in the spring? Think about it. How much will be the extension in the spring? I'll tell you one simple thing. This problem is very similar to this string problem which we did some time back. 30, 30 from here. What is the tension in the spring? It was just like one was the supporting force, one was the pulling force. So don't think the extension is 0 or maybe the double of, don't think the force is 60 Newton. No, don't think like that. Actually speaking, the spring force is 30 Newton. Spring force is 30 Newton. One will act like the support, other will be pulling it. One supports it, other pulls it. Without the support, the whole thing will fly off. So that's the reason why spring force is 30 Newton. Spring force magnitude wise is kx. K is nothing but 100. So 100 into x is basically 30. 0, 0 cancels. So x is basically 3/10th of a meter. Yes, 3/10th of a meter. 0.3 meters basically, or 30 centimeters. Understood, guys? Many people say the answer is 0 or 6/10 Newton. That is not correct. It is 0.3. Yep. Very good. So these are some of the interesting spring problems which we have. Let's proceed ahead. Let's proceed ahead to some pulley related questions also. So you might have seen in many questions pulley also comes into play. Now whenever pulley comes, what a pulley does is basically, if there is a rope wrapped around it, imagine there is a rope wrapped around it. There is some rope which is wrapped around it. What it does is it just changes the direction of the tension, nothing else. This rope, okay, from this side might be pulled by some tension like this. The same tension continues. Now it pulls here. This rope might be pulling some object like this. This rope might get pulled in this direction. And the same rope will be pulled in this direction like this. So the job of the pulley is basically to change the direction of the force. To change the direction of that force, more specifically the tension. Okay. And our pulleys are ideal. So ideal pulleys, they will, not have mass. They have no mass and are completely smooth. So no friction which is involved over there. So they don't have masses, nor do they have friction or rubbing forces between them. And these pulleys will be probably held over here somewhere like this. Maybe it could be supported like this. So these are the kind of things you might be seeing it in different problems. Let's start seeing some pulley based questions. Okay. All that you need to remember, the direction of tension will change. That's all. Accordingly, you will adjust the problem. The most important problem in a pulley problem is this particular system which is called as the Atwood problem. This Atwood problem is very, very important. What happens is you have a pulley. This pulley hangs from a roof and there is a rope which goes around that particular pulley. There is a rope which goes around this particular pulley like this. And on this side there is some mass and on this side there is another mass. You can assume any mass to be more, any mass to be less, doesn't matter. In this particular scenario, M2 is more. So if M2 is more, what will happen is M2 will go down. It will have some acceleration. Because M2 goes down, it pulls the string. This string passes over that pulley and this mass gets lifted up by the same acceleration. So this mass number 1 goes up by the same acceleration. There will be some tension. I have to find acceleration, tension, everything in this particular question. So let's try to solve this. Let's try to solve this particular question. Everybody understood till this point what we have to do? We have to find acceleration. One of the masses will go down, one of the masses will go up. That's all. Cool. The heavier mass goes down, the lighter mass will go up. So what do we do? Start by showing the forces on each masses separately. On the mass number 2, the weight will act, so it will be m2g. On this mass also the weight will act, so it will be m1g. The same string continues, so the same tension continues. This mass will be pulled by the string. Remember, tension acts always away from the body. This is the body, so it acts away. This body, so it will act away. So the tension always acts away from the body. Away from the body. These are the only forces, nothing else is there. Nothing else is there in the problem. Okay. So if you show the forces, the next step is equations. For this mass, T is more than T is in the direction of A, M1G is opposite to A. So I will say T minus M1G is equal to M1 into A, is equal to M1 into A. Net force is mass into acceleration. For this guy, M2G is in the direction of acceleration. So M2G minus T is equal to mass into acceleration. Is equal to mass into acceleration. That's about it. Now we'll solve the question. That's it. The best way to solve this particular question, you can see, I can add both of them. I can just add both these things. If I add both these things, tension cancels, these two get added up. So M2G minus M1G is equal to M1A plus M2A. Take A common. Here take G common. Now acceleration will be basically G times M2 minus M1 upon M1 plus M2. That's it. That is the answer. So what did we get the acceleration as? It was G into the difference of the masses, the difference of the mass upon the sum of the mass, upon the sum of the masses. That is what we got the acceleration as. Is it absolutely clear? Yep. This is how you can solve the question. But we don't stop it over there. We want to find the tension also. So to find tension, either use this or use this. Completely up to you. So maybe somebody will say, I want to use this equation. No issues. So it will be M2G minus T will be equal to M2 times acceleration. What is the acceleration? It was G into big mass minus small mass difference upon the sum of the masses. Okay, let's take tension here, take these people over here. So therefore tension will be M2G plus M2G into M2 minus M1 upon M1 plus M2. I've just taken this guy over here, but putting this minus sign is important. T over there, these people over here. So M2G minus this whole thing over here. I can clearly see M2G is common and it will be 1 minus this, 1 minus M2 minus M1 by M1 plus M2, which will be M2G. Now see what will happen. Denominator will be M1 plus M2. Numerator will have, let's see, numerator will have M1 plus M2 minus M2 plus M1, because minus minus will become plus, minus minus will become plus. This will be M1 plus M2. So M2 M2 cancels, so it will become 2M1. So it will become 2 times M1 into M2 into G, the whole thing divided by M1 plus M2. So that is the value of tension. So this is the tension in the rope. Simple. The pulley 2 have masses. Why we did not consider it? King Money will consider it in rotational motion, not here. In rotational motion, we'll consider the pulley's shape, size, as well as the mass, all the three things. Right now, we have not learned the theory of how to solve rotational problems. That's why we ignore the pulley's mass. It's there, but we are ignoring, or we are assuming the pulley's mass is much, much smaller as compared to the block's mass. This might be 7-8 kgs. This is maybe 500-600 grams. Then we neglect it. It's okay. Is that okay, King Money? Right. Now, there is one more part to this, and that is this roof is holding that pulley. The roof is holding that pulley, so it will be applying some force on that pulley. How much force does the roof apply on the pulley? So, to think about it, if I just consider the pulley and the support system along with this string, I will say that the string wrapped around that pulley pulls that pulley from both sides with the force of tension. T and T down, the rope pulls that pulley down. The roof holds it with some force of F. It's the force by the roof. It's like holding it by some normal or some push-pull mechanism, whatever. That's it. This entire thing right now is at rest. It is at rest. How is the pulley moving? It is just there. It's the rope which is sliding over it. So therefore, can I not say F is equal to 2 times of T? Can I not say F is equal to 2 times of T? But tension value, we already got it over here. 2 m1 m2 upon m1 plus m2 whole thing into G. 2 times m1 m2 upon m1 plus m2 into G. Therefore, it is 4 m1 m2 G upon m1 plus m2. That is the force by the ceiling on the pulley. This kind of question can also come in the examination. This kind of question. Okay. So we have found the force on the ceiling. We have found the tension in the rope. We also solved the problem for the acceleration of the masses. Another beautiful question, guys. Another beautiful question, guys, coming up on your screen. Imagine there is a pulley over here. In this particular problem, question is to find the acceleration of the 3 kg mass. Question is to find the acceleration of the 3 kg mass. How do we do this question? Obviously, start by drawing the free body diagram of the 3 kilo mass. Nothing else to do. Okay. So 3 kilo mass. What are the forces? I will say, obviously the weight is there. So 3g downwards. The tension is acting up. So I'll show tension upwards. Tension always pulls the body. So it has to pull and it always acts away from the body. Perfect. So it is also accelerating. I'll just show the acceleration like this. But there is a problem. See, if I write the equation, tension is in the direction of acceleration. 3g is opposite it. So it will be mass into acceleration. I do not know the value of tension. So I'm stuck over there. But no issues. If I draw only the free body diagram of the pulley, you will realize the center point is being pulled by 90 Newton. The string which is wrapped around it pulls this pulley down by the force of tension on both sides, T and T. So therefore, I can say 2 times of T is 90 or tension is basically 45 Newton. Take that value and put it here. That's why drawing FBD is very important. Choosing the system is very important. If I did not choose pulley as a system, I would never be able to solve the problem. So 4 minus 30 is equal to 3a. Why 30? Because G is 10. Sorry, 45 minus 30 is basically 3a. So 15 is equal to 3a. Therefore, I get the acceleration as 15 by 3, which is nothing but 5. So 5 meters per second square is the answer. Is it clear, everyone, how we got the answer? Yep. Great. Awesome. Awesome. Let's go ahead to the next question coming up on your screen. Okay, so this system is there, everything is smooth, no friction at all. You can see there is a pulley over here at the edge and this mass is on a flat surface, small m, and this 4m mass is on an inclined surface. So what will happen, this heavy mass is going to go down, slide down. So it will end up pulling the string and in return this mass will end up going towards the left. Question is to find the acceleration of the masses. That's all, nothing more. Okay. What do? Always FBD. That has been our bread and butter. That is what we have been doing throughout the session now. So let's start by drawing the free body diagram of M mass and 4M mass, both. I will need both of them. Okay. So starting off with M mass first over here, and then I will show 4M mass. But remember one thing, 4M mass is at an angle. So I'll show it like this. Okay. On M mass, weight is there, of course, mg. Normal is also there. Let's say I call it N1. And there is one tension which will pull like this. And the result of this is the acceleration. So there is some acceleration also. So if you write the equation for this guy, there is only one force in the horizontal and the acceleration is there. So T will be equal to mass, which is M into A. That's all. Nothing else is there over there. In the vertical direction, no point writing, because what will it do? Even if you write, it will be like N1 is equal to mg. No use of this. There is no use of this equation. Even though it is correct, no use of this equation. So let's go with 4M mass. Since it is at an angle, I know that I will have to split my mg force eventually. My mg force, I will have to split it. There will be one normal force over here. Let me call it N2. This string will pull you up like this. So it will be T, because it's the same string. Always tension acts away. And as this moves, this goes down. So obviously acceleration will be down the incline. Okay. Use our standard technique, guys, which I have been telling you. Splitting it into 8 method. Split it into 8 parts. Split it into 8 parts. That's all. Come on. Let's do this. Let's do this. Okay. So guys, who is angle theta from this? This is 30. So naturally, this angle is 30 degree. This is the inclined plane angle. Inclined plane angle. Oops. That is 30 degree. So naturally, even this is 30 degree. Even this is 30 degree. Even this is 30 degree. All these are 30 degrees angle. So naturally, I can see mg's component, which is going to be here, will be mg cos 30, and the mg's component, which is down here, will be away from theta or 30. So it will be mg sin 30, which is actually mg divided by 2. Sin 30 is half. Perfect. I don't think I will write any equation in the vertical direction. I will go along the incline. That will be better. So along the incline, I can just say mg by 2 helps in the acceleration. Tension opposes it. So this is the net force is equal to mass into acceleration. Mass is 4m. Acceleration is basically A. Acceleration is basically A. So that's it. Tension I already know is ma. Tension I already know is ma. So this is equal to 4 times ma. So this is mg by 2. So therefore, mg divided by 2 is equal to 5 times of ma. Therefore, acceleration is, you can see that mm cancels, it will become g by 10, which is also 10 by 10, which is 1 meter per second square. 1 meter per second square. That is the answer. Absolutely clear, everyone? Like you can see again and again, if you follow proper routine, proper mechanism, proper system, it is very straightforward. You have to go step by step. You cannot hurry or skip any steps. Shall we go ahead to the next question, guys? Okay, of Newton's laws. Okay, this is going to be very, very interesting again. All right. So what do we have? We have a pandu whose mass is 40 kg and he is holding a rope. He is holding a rope which goes like this over a pulley which is supported by a roof. That rope is indirectly again connected to a platform whose mass is 20 kg. Whose mass is 20 kg. It's a very interesting problem. Obviously, if pandu leaves the rope, what will happen? The rope will fly off, this rope will come down, the platform will come down, everybody will fall down. That's it. The end of story. Then there will be no problem only. Correct? But we want a problem. So we want a solution also to that problem. And the problem is, we have to find how much force does pandu apply on the rope. How much force does pandu apply on the rope? What is the normal reaction between them? So these are the kind of forces that we want to calculate. What force does pandu apply? What is the force which pandu applies on the platform? All these things. Assuming this entire system is at rest. Assuming this entire system to be at rest. So we'll solve it for the rest case. Now we have to think whose FBD should we draw. See, if you are interested in this normal force between them, obviously we should make normal as an external force. So you have to probably draw the FBD of pandu separately, 100% sure. So let's do one thing. Let's show only pandu first. Let's show only pandu. Pandu is over here like this and he's holding that rope. On pandu, the forces are, number one, his own weight. Obviously 20 g will not act on pandu, 40 g will act. So 40 g will be the weight force on pandu. He's standing on the platform, so obviously there will be a normal force. Obviously there will be a normal force, guys. So just like 40 g, you also have a normal force on the legs of the pandu. I'll call it N. I think there is one more force. Observe carefully. That rope which is there, which goes around it. That rope which is there, which goes around that particular pulley over here. Okay. That rope will be pulled down by pandu and that pull will be the tension. Pandu pulls the rope with a tension and that other end will also be pulled like this by tension. Think about it. A rope will always be pulled. Tensions are always away from the body or the element. So you can see tension is always away. Pandu is pulling. This is the pull of pandu. This is the pull of pandu downwards. If I call this force as the action force, if I call this force as the action force, pandu pulls it by 3 Newton, then the rope also pulls pandu up by 3 Newton, which will be then the reaction. So hence the reaction force on pandu will be up. So on pandu tension will be upwards. So a lot of people miss this particular force of tension. Miss this force of tension. Be careful. Okay, now it is fine. Tension and your normal force together balance how much? 40 g. Tension and normal together basically balance 40 g. So this is sorted. This is sorted. But the problem is I don't know normal nor do I know tension. So I need to rethink and resolve the problem. Maybe it's some other way. Okay. What if I draw the free body diagram of that plank? What if I draw the free body diagram of that particular plank? Okay, that plank is basically 20 kg. The plank is basically 20 kg. So the force of weight, gravity, sorry, will be 20 g downwards. This normal, again, if I call this normal as action force, who is applying it? Plank, the platform. On whom? Pandu. Where will the reaction be? Where will the reaction be? On the plank. Who will apply? Pandu. So pandu pushes the plank down with the normal force. Because he's standing on it, normal will act down on the platform. Everybody clear absolutely about this? Okay. Also do not forget, this tension is there over here. This tension is being pulled. Basically the string is being pulled by the tension from this point over here. The platform is pulling it down. So it will also pull the platform up like this. This is the tension. N acts down, T acts up, 20 g acts here. Why did tension act here? If this is action, this is reaction. Why did normal act down? Because if this was action, this was reaction. Equal and opposite, different bodies. Newton's third law. Wow, perfect. So if I write the equation over here, how will it look? It will look N plus 20g is equal to T. N plus 20g is equal to T. Oh, now I have two equations, I can solve it. I have two equations, I can solve it, guys. So if you want, put the value of tension over here. Put the value of tension over here, whatever this tension is, right? Just substitute it over here. So it will become N plus 20G, N plus 20G plus the normal is equal to 40G. So you can see basically from this, you can see that you will get 2N is equal to 40 minus 20, which is 20G. Therefore, normal is basically 10G, 100 Newton. Normal is 100 Newton. So just substitute 10G over here is equal to T. Therefore, T will be nothing but 30G. So Pandu applies a force of 30G, which is 300 Newton on the rope, and the normal force between Pandu and the platform is basically 100 Newton. That is the solution. Is that absolutely clear? Wasn't this a fascinating, interesting problem? These kind of questions also you can get. Great. Now, this is done, okay. Great. Yeah, I think now what is left in this particular chapter is that multiple pulleys, then pseudo force, then static and kinetic friction, and then block on block questions. Okay, so these four things we will be doing it in the next class. Today we have done all the standard questions on blocks with blocks pushing each other or over each other, strings pulling multiple blocks, pulley block system problems, spring problems, all these kind of questions we have done today in the part 1. We will be continuing this lecture in the part 2. Okay, for now this much is enough. We will continue ahead in the part number 2. Cool. Chalo. Have a great time. I hope you had a lovely afternoon learning these concepts, and do not forget to leave the comments waiting for part 2 or part 1 done in the comments. Okay, I want to see your attendance, and yeah, do not forget to like the session and subscribe to the channel. Bye bye. Take care. Have a great time.